Okay, so picture this scenario. It's it's Tuesday morning, you are running late, and you absolutely cannot find your cell phone.
Oh, a classic panic. We have all been there.
Right. It is somewhere on your living room table, which is currently just a total disaster zone. You've got
Yeah.
stacks of mail, three different coffee mugs, your keys, maybe a cat sitting there. You're panicked.
Naturally.
And then your brain does this weird thing where it just snaps into this like search mode. You know your phone case is blue, so suddenly every single blue object in that messy pile just seems to vibrate. It pops right out at you.
Yeah, that universal where's my stuff instinct kicking in.
Exactly. But here's the thing that always keeps me up at night. What is actually happening in the wetware of my brain when I do that? I mean, am I just visually shouting "Beelaliwi" at my retinas? Or is there some complex calculus going on that actively suppresses the coffee cups and the junk mail?
It's a really fascinating question. And for a long time, we've had theories about this biological attention mechanism. We know that attention changes how neurons fire, but testing how it actually optimizes a search in a living, squishy human brain is incredibly difficult.
Because you can't just open someone up while they're looking for their keys.
Right. You can't exactly hit pause on a human, tweak a single neuron sensitivity to blue, and then see if they find their phone a millisecond faster.
So usually we just look at fMRI scans and make these, educated guesses. But today, for this deep dive, we're looking at a study that took a completely different approach. We're getting into a paper by Grace Lindsay and Kenneth Miller titled How Biological Attention Mechanisms Improve Task Performance in a Large-Scale Visual System Model. And I think the key word there is model.
Spot on. They didn't use a human brain. They didn't use a monkey brain either. They used a deep convolutional neural network, specifically one called VGG16, as a stand-in for the primate visual system.
So we are effectively using AI to figure out how we see.
In a way, yeah. And what they found really challenges some of our basic assumptions. It turns out that simply turning up the volume on what you're looking for might actually be the completely wrong strategy, depending on where in the brain you do it.
I love this concept. We've got digital brains, lost cell phones, and this sort of battle between what neurons want to do and what they should do. So let's unpack this. First off, introduce us to the subject. Who, or rather, what is VGG16?
Well, VGG16 is a bit of a celebrity in the machine learning world. It's a deep neural network trained on ImageNet, which is this massive database of millions of images. So it knows what a clock looks like, what a greenhouse looks like, what a spider looks like.
So it's seen the world, basically.
It has. But the reason neuroscientists like Lindsay and Miller love it isn't just because it's smart. It's because its architecture eerily mimics the hierarchy of our own visual system. It has 13 convolutional layers.
Meaning it processes visual information in distinct stages.
Right. Think of it like a corporate hierarchy. The early layers, so layers 1 through 4, are kind of like the entry-level workers. They handle the raw data. They spot edges, lines, simple textures. This corresponds to the primary visual cortex, or V1, in our brains.
Just doing the grunt work, like I see a vertical line, I see a curve.
Precisely. And then you move up the ladder. By the time you get to the executive suite layers 10 through 13, the network is putting those pieces together. These layers act like the higher visual areas in a primate, like V4, or the inferior temporal cortex. That's where those lines and curves actually become a face or a toaster.
Okay, gotcha. So we have this digital twin of the visual system. What did they actually make it do? Did they just show it pictures of cats and dogs?
No, they made it struggle. Remember your cluttered living room table?
Yeah.
They recreated that mathematically. They took images of specific objects, let's say a clock, and they created these merged images. Imagine taking a photo of a clock and a photo of a greenhouse, making them both semi-transparent, and just overlaying them.
So it's just a ghostly, confused mess of pixels.
Exactly. They also created what they called array images, which are just grids of 4 different objects.
Okay.
And the challenge for the AI was simply find the clock. But the kicker here is the network wasn't retrained to handle this specific mess. It had to use attention to filter through the noise, just like you do with your phone.
Which brings us to the core mechanism of the study. They tested something called the Feature Similarity Gain Model, FSGM, which is a mouthful, but my understanding is that this is basically the dumb rule of attention.
It is the dumb rule, yeah, but it's also very elegant. The theory basically says if a neuron likes a certain feature, say the color blue, or a vertical line, and you are currently looking for that feature, your brain should just turn up the game on that neuron.
Literally like a volume knob. If I want to find the blue phone, I find every neuron that gets excited by the color blue, and I multiply its activity. I boost the signal.
That's it. It's a multiplicative modulation. And inversely, if a neuron hates blue, maybe it only loves red, you turn it down.
I mean, that sounds incredibly intuitive. If I want to hear the bass line in a song, I turn up the bass on the equalizer. If I want to find the phone, I boost the blue neurons. Why would we even think it works any other way?
Well, that is the mission of this deep dive. Does that simple rule actually work? When Lindsay and Miller applied this dumb rule, just boost what you like, did the VGG16 network actually get better at finding the clock in those ghostly images?
I'm guessing the answer is yes, but
The answer is yes, absolutely, but only if you apply it at the very top of the corporate ladder. When they applied this boost to layer 13, the executive's performance skyrocketed. We saw a 19% increase in performance for those ghostly merged images and a 23% jump for the array images.
wow, that is massive. That's the difference between finding your keys instantly and being late for work.
Huge gains. But when they applied that exact same rule to the early layers, the entry-level workers in layers 1 through 4,
Let me guess, crickets.
worse than crickets. It was totally negligible, and in some configurations, it actually hurt performance.
Okay, this is the part that really surprised me in the reading. Because you would think boosting the raw materials, the lines and edges that make up the clock, would help the system build a better picture of the clock from the ground up. Why does boosting the early layers fail so badly?
This leads us to the most critical insight of the entire paper. It's this battle between tuning and gradients.
Okay, let's stick with the corporate analogy here. Tuning versus gradients.
Right, so tuning is just the neuron's personal preference. Like, I am a neuron and I love vertical lines. It's just what the neuron naturally responds to.
The entry-level worker saying, I'm really good at filing papers.
Right. Now, gradients in the context of AI and calculus represent optimization. The gradient mathematically tells you how a neuron's activity should change in order to minimize error and get the right answer for the whole system.
So tuning is what I like to do, and gradients are what the company actually needs me to do to win the contract.
Perfect analogy. Now, in a perfect world, those two things would match. If I like clocks, boosting me should help find clocks. But the study found that in the early layers, tuning and gradients are often not correlated. Sometimes they're even negatively correlated.
Negatively. Wait, so the neuron is saying, I see a vertical line, which is part of the clock, but the gradient is saying, shut up, you're confusing us.
Exactly. Think about the cluttered table again.
Yeah.
You are looking for a clock. A clock has vertical lines, but the greenhouse next to it also has vertical lines, and the stack of mail has vertical lines.
Oh, I see. So if I boost the vertical line detector way down in layer 1.
You are boosting the noise just as much as the signal. Or worse, you're actually boosting the distraction more. The entry-level worker is shouting, I found a line, but he's actually pointing at the greenhouse.
And that completely confuses the executives upstairs.
Precisely. The signal just gets scrambled because the feature of vertical line is too simple. It's ambiguous. It doesn't align with the network's ultimate goal of distinguishing the clock from the greenhouse.
But when you get to layer 13,
At layer 13, the neurons are tuned to highly complex concepts. A neuron up there might be tuned to actual clockness. So if you boost that neuron, you are directly boosting the solution. Tuning and gradients finally align.
okay, so the dumb rule of just boosting what you like only works when what you like is specific enough to actually be useful.
Exactly. And this explains something they observed called the wearing off effect.
Which honestly sounds like a headache medicine problem.
It kind of is, computationally. They did this analysis where they stimulated layer 2 way back at the start of the visual stream, and then tracked that attention signal as it moved through the network all the way to layer 13.
Like tracking a memo from the mailroom up to the CEO.
And the memo got completely lost. By the time the signal propagated through all those nonlinear layers, the boost had just dissipated. The information was washed out.
This is so interesting because biological experiments do actually show attention effects in the early visual cortex, right? Like we see V1 lighting up when monkeys pay attention to something. But this model suggests that activity might not actually be doing the heavy lifting.
Yeah, it creates a real puzzle for neuroscientists.
Yeah.
It implies that the early modulation we see in biology might just be a side effect, or maybe it's doing something we don't fully understand yet. But regarding the specific task of object detection, the heavy lifting happens at the top.
There's also this debate you hear about in neuroscience, feature matching versus FSGM. Does this study pick a winner there?
It actually suggests a bit of a truce. So feature matching is the idea that you only boost a neuron if the thing in its field of view actually matches what you want. It's highly precise. Whereas FSGM is the blunt, boost everything globally approach.
Like a smart bomb versus carpet bombing.
In a way.
Mm.
But what the study showed is that if you apply the blunt FSGM rule at an early layer, by the time it propagates to a later layer, it actually looks like feature matching.
Wow. So the mechanism literally changes appearance as it moves through the hierarchy.
Yes. It suggests that conflicting data from different labs might just be a result of where exactly they are sticking their electrodes.
Yeah.
V4 versus frontal eye fields. You might just be seeing the downstream effect of a very simple upstream rule.
I want to pivot a bit to the cost of this attention, because getting a 19% boost in detection sounds amazing, but in biology, nothing is ever free. If you turn the volume up too high, don't you get feedback or static?
You get hallucinations. This brings us to signal detection theory. You have true positives, which is spotting the clock when it's actually there, and false positives thinking a toaster is a clock.
Oh, I've definitely done that. Looking around going, is that my phone? No, that's a coaster.
Right, that's a false positive. So the researchers played with the overall strength of the attention. They call it the beta value.
The master volume knob.
Right. And they found this sweet spot. At moderate strength, you get that beautiful jump in true positives without a spike in false positives. You find the phone, but you don't hallucinate phones that aren't there.
But what if you crank the knob to 11?
The trade-off completely collapses. The
Yeah.
true positives plateau because you've already found all the actual clocks,
Yeah.
but the false positives just skyrocket. The AI lowers its criteria so much that literally everything starts looking like a clock.
It's just too eager to please.
Yeah. And here is where the model gets scary accurate.
Mm.
The firing rate changes required to hit that exact sweet spot in the model were about 5 to 7%.
5 to 7%. That seems suspiciously specific.
It is. Because when we look at actual biological recordings of V4 neural activity in macaque monkeys performing similar tasks, we see, you guessed it, about a 5 to 7% change.
That is incredibly validating. You have a silicon brain trained on JPEGs, and it converges on the exact same biological constraint as a living primate brain.
It's wild. It suggests that VGG16, despite just being code, is capturing something fundamental about the mathematical limits of visual processing. The model also replicated the finding that spatial attention looking at a specific spot increases your overall sensitivity, while feature attention looking for a specific quality mostly just adjusts your criteria or your thresholds.
So spatial attention clears up the image like a camera lens, but feature attention just makes you a bit more trigger happy.
Basically, yeah. Feature attention shifts the representation of everything slightly towards the target. It makes the haystack look a little bit more like a needle.
Okay, so we've established that the dumb rule FSGM works best at the top of the hierarchy because that's where the neurons actually know what's going on. But this leaves a massive question hanging over us. Does the human brain actually use the dumb rule? Or are we fundamentally smarter than VGG16?
That is the million-dollar question. Does the brain use FSGM just because it's hardwired and computationally easy? Or does the brain somehow calculate gradients like, does it optimize perfectly for the specific task at hand?
Can the squishy human brain do calculus on the fly?
Right. And Lindsay and Miller actually proposed an experiment to finally settle this. It hasn't been run yet in a lab, but it's a brilliant setup. They suggest using 2 different tasks with the exact same visual cue.
Walk us through it. How would this work?
Okay, so task A is orientation detection. You show subject a vertical line and ask, is there a vertical line present?
Simple enough, yes or no?
And then task B is color classification. You show them the exact same vertical line, but you ask, what color is the vertical line?
Okay. But in both cases, I have to pay attention to the vertical line.
Correct. You are attending to the exact same physical feature. Now, if the brain uses tuning the FSGM model, the attention signal should look absolutely identical in both tasks. The neuron likes vertical. You want vertical, so you boost vertical. The dumb rule doesn't care why you want it.
It just knows vertical is good right now.
Exactly. But if the brain uses gradients, if it effectively calculates what is mathematically needed for the specific goal, the neural signal should be different.
Because detecting presence and classifying color are entirely different computational problems.
Precisely. The gradients, the optimization path to get the right answer would be different. So if we record from the neurons and the activity looks different for the 2 tasks, we know the brain is smart. It's optimizing based on the goal. But if the activity looks exactly the same, the brain is just using the dumb rule.
That is such a clean test. It cuts right to the heart of whether our attention is this flexible, intelligent tool or just a rigid biological lookup table.
It really is. It's basically a challenge thrown down to the experimentalists. Like, here's the map, go find the treasure.
I love that. Using AI to design the experiments that will ultimately decode biology, it feels like we're closing the loop there.
It really does. We used to look at brains to try and build better AI. Now we are using AI to understand the brain.
So, to wrap this up for everyone listening, when you are searching for that lost phone on the messy table, what's the ultimate takeaway here?
The takeaway is that your sense of focus is likely a massive top-down process. The decision-making parts of your brain are shouting buoy and rectangle, and that shout is most effective in the high-level visual areas, the executives where object identities are actually formed.
Up in layer 13.
Layer 13, exactly. By the time that signal filters down to the raw data in your eyes, it might be weak or completely scrambled, but that doesn't really matter. As long as the high-level concepts align, you find the phone.
But here's where it gets really interesting for me, and I want to leave you with this final provocative thought. VGG16 is a feed-forward network, right? The information only goes one way, bottom to top.
Right, it's a strict one-way street.
But real human brains are these messy interconnected webs. We have skip connections where layer 1 talks directly to layer 10, and we have massive feedback loops from top to bottom.
Oh yeah, the brain is definitely not a one-way street.
The paper mentions that in the later layers, the tuning and the gradients align, but is it possible that in a living brain, the top-down feedback actually teaches the early layers to align over time?
That is a deeply fascinating possibility. You mean, what if the brain effectively rewires itself so the dumb rule actually works better?
Exactly. The authors briefly mention anti-Hebbian learning. Maybe over time, if a high-level executive neuron realizes that the entry-level guys are confusing it, it sends a signal back down to change how they report the data.
So if you search for enough clocks in your life, your early visual cortex actually learns to filter out the vertical lines of greenhouses at the entry level.
Yes, it implies that attention isn't just a spotlight we shine, it's a skill. If the brain can learn gradients, maybe our attention systems learn to be smarter over our lifetimes. We might effectively be rewiring our early visual cortex to perfectly align with our daily goals.
So you aren't just paying attention, you are literally training your brain to be a highly optimized phone-finding machine.
Which honestly gives me some hope for my ability to find my keys tomorrow morning.
You just need a little more training data.
I'll get right on that. This has been such a fascinating look at the intersection of AI and neurology. A huge thank you to Lindsay and Miller for this incredible study.
It was an absolute pleasure digging into it.
And thank you for joining us on this deep dive. Stay curious, and we'll catch you next time.